Welcome to another Great Cow Basic tutorial stroke demonstration of the 16F171 chip family. Hello, my name is Venn. I'm a co-developer at Great Cow Basic and I'm taking you through the slides. So this is part 18. This is the 18th video that I've released on the 16F171 chip family. 2 more to go. What we're looking at today is assembly and alternative assemblers and how you can use other alternative assemblers beyond Great Cow Basic. Let's recap where we were and what this is. So Great Cow Basic is an open source compiler. It supports PICs, AVRs, and LGTs from Logic Green, their AVR microcontrollers. We've extended the libraries to support the 16F171 chip family. But Great Cow Basic is a truly cross-platform with common code translation. I've explained that in the previous tutorial, that your user program can be translated into many different target architectures. Any of the PICs, AVRs, LGTs, but within there are subgroups and subgroups, and it will handle that to the greater case. If your code is generic, it will work. If you're using explicit registered, then you need some care, but it's all resolvable. What am I using and have been using? I've been using the Microchip low pin count demo board, and I've inserted into that a 16F17126. You can build your own on the bread count board, on the breadboard laid out by Chris Roper from South Africa. So what we're going to do is I'm going to show you this straight away. We're going to create a program. We're going to save that program, and then we're going to load that program into MPLAB-X as an alternative assembler and programming interface. And then we can debug it as proof that you can do this. So you can take source code from Great Cow Basic and use it within other tool chains. It's extremely flexible, and it's not that hard. It's only 4 or 5 steps to make it work. I'm going to be using and plugged into the program on my PIC Kit 2 is a 16F17126. So let's recap what we saw. Great Cow Basic is a soup to nuts source code compiler. It uses the libraries. It will take you through the preprocessor, code translation, assembler, and linker, and it will create an absolute machine code hex file for the target chip. However, as I said yesterday in the previous tutorial, you can actually intercept and pick up the assembly language file and put that through your own toolchain. In this case, I show a linker, but it's actually going to be MPLAB IDE. So what we're going to do is we're going to review and create a really simple program. We're going to create a project inside MPLAB-X. We're going to add in that source file that we've just created back in Great Cow Basic. We are going to set the simulator up, then set the programmer up, and then finally we'll test compile the program inside of MPLAB-X just to prove it all works. So I've got different things laid out. I've got the board laid out with nothing in it, and I've got other pieces of software ready for us to use. Now, I'm going to just come out here of my PowerPoint for a second because I just need to make sure that I've got everything set up to make this work nice and smoothly for us. There we go. Great. So here we go. I'm going to go in Startup, GCStudio. I'm going to start it up, and I'm going to go and continue without code. Oh no, I won't. I'll go over to where we were working previously in our demonstrations. Great. I'm going to shut that down. I'm going to create a new file. You can see I've been working on my own. File, new text file. And then it says select a language at the top. Let me zoom in on that for you. Select a language. And the language to select is GCB. And it will then turn on all the attributes into there. Let's just save that for the time being. Even though it's an empty file, I'm going to save that as 310 using MPLAB. Okay, all lowercase. MPLAB-X.GCB. So I've created an empty file. Okay, we're going to use some snippets and we're going to create a program quite quickly. And that program is going to just flash the LED. So it's extremely simple, nothing too hard. We don't want it too hard for the purpose of what we're doing. So underscore will enable me to type in a header. So I will turn on screencast so you can see that. Underscore H, it will automatically put you a header into an empty file. This program shows integration. Tab, I'm going to put my name in. Tab, version 1.0, and today's date is already shown. So the header comes from snippets inside of the IDE. Underscore chip. It inserts the header 16F17126. It's not, what's the word I'm looking for? It's not case sensitive, so that's fine. Enter. I'm going to create a constant. We know how to create constants. Hash define LED 1 is on port C.0, and that's where my LED is attached to. We've been working on that. dir LED 1 is an output. So I set my constant to an output. Right, I'm going to use some code. Let's have a think what I'm going to do it. Underscore do. I want a do loop. I can select a do loop. Automatically puts it in. LED 1 equals not LED 1. We've seen this in one of the very first demonstrations. So I've now got a working piece of code. I can now program that. And what we'll do is we'll look out in the lab to see what it does. There we go. I just pressed hex and flash icon. Told me that the LED is not as correct. I've got an error. We've not seen errors before, so let's have a look at the problem. If I click on the problem, it will take me to the offending line. LED is not defined. That's fine. It's actually called LED 1. I've just pressed F5 to reprogram it. That's good to see an error. And now what we've got is an LED flashing. Now I haven't put a delay in it because when we go into debug this, we can see it a little bit quicker. I don't want the wait. It's not a lot of code, but it's just a distraction to what we're trying to do. So we know we've got a working program. So what I'm going to do is I'm going to set this up for integration into MPLAB. I'm just going to ensure I have got in my program of preferences. Let me go to preferences. Compiler is set to PIC18. It is. Press OK. It is generating code for PIC18. So if I press function key F4 and I type in .s or s, it says open S, and that is the source file for MPLAB that we want to be using. So this is a source file. It's called a .s file. It's an assembly file ready for MPLAB-X. So this is our file. Let's just go into MPLAB-X for a second. There we go. Great. There's the source program, and on the left, I've got MPLAB-X. So let's walk through the process. The process is in your PowerPoint, so you don't have to remember it, but I've actually got it on the screen. So File, New Project. I'm going to create an embedded standalone project, select it. Select the chip family name. I've already got it pre-selected in my recently used, and select the simulator. So I've got as a device PIC16F17126. Next. Now, because we're generating it for PIC-AS, expand PIC-AS and take version 2.4 and give it a file name. I'm just going to use the chip name, okay? Because then I know which chip it is. You can use whatever name you want. Finish. It's now created a project. What we now need to do is add in our .s to this file. So I'm going to go back into GCStudio, take the file name by copying the file name out. Inside MPLAB-X, source files, click on it, right-hand mouse button, add an existing item, paste in the .s file, which is the name of the file, 310 underscore using MPLAB-X.s and select it. It has now put it inside and it's now compilable. Two changes I want you to make. Go to your project, right-hand mouse button, into properties, and because you want to see it working at the right frequency, you really should go into the simulator and set the instruction frequency to 32, because that's what it will compile that. Apply that. If you want to program it, then go to the PowerPoint and pull out the command string that we're going to add in into this option called building. Execute this line after build and then paste in the PIC-kit command line that we want it to call to program our chip. Now it says ... here because you just need to add in wherever you've got it installed. Okay, and I can't remember where we installed it, so I'm just going to replace that ... with my installation folder. And here we go. So it's actually installed in GCStudio demo, then it's the command line. Press OK. We've now created a project. Let's just see if it compiles. To do that, for those who don't know, you can go production, build main project, or press function key 11. It will now compile it. It has compiled it. It is now programmed it. I think it's programmed it. Let's prove that. PIC-kit plus, user interface, erase the chip. Press F11 inside of MPLAB. And if the LED comes on, we know it's programmed it. Excellent. So we now have got a program that we can use, and it's completed. Let's do some debugging. Take the debug option in MPLAB-X, discrete debugger operation, and build for debugging main project. Because we told it to program it, it's done the programming. Then to walk the program, to debug the program, discrete debugger operation, debug discrete debugger operation, launch the debugger main project. Now loading the source files, and we're actually in the debugger, and we can walk the program using the debugger codes. Now what we can do, we can look at our source program and we can see exactly what's happening. So let me walk you through to the piece in here where it sets up dir LED out. Well, it clears, it needs to set LED or the TRIZ on this particular register. I'm going to walk that through. It's done it. And then it's going to the LED1, not to LED1. And here it is. It's actually doing it. Here, it's walking the code as I'm pressing F7, and it goes back to number 7. So it's going around in a circle, doing the instructions that were laid out. Let's look at that in terms of variables. Here's lat_c in the debugger, in the variables register. And if I walk the code, you will see a lat_c value change. And that shows us that the code we've generated is correct. Set it to 1, that means the LED is on. Sets it to off as I walk the code. I am not going to teach you the debugger, just show you the fact that that's happening. Let me stop the debugger. Let me change my source program in GCSBASIC to change the LED to port C1. If I look at my source program in here, I will see my source program is set to port C.0. I'm going to compile my GCSBASIC source where I've changed my port ID, and it's now changed it inside of MPLAB. Debug, discrete debugger operation, rebuild it because we've changed it. We've changed our source. Debug, let it finish programming. Debug, discrete debugger operation, launch debugger main program. And now we are in our source program, but this time when we walk at the program, I'm going to put a debug halt here. Here we go. Here we go. If we look at our variables now, you will see that lat C values are accordingly changed because now we're setting up bit 1, not bit 0. C.0 versus C.1. So what we're getting here is quite sophisticated operations in terms of the debugger. And you can walk very large programs using the Microchip MPLAB debugger to see what's happening to your source code. So you can actually walk the code and use a completely different environment to compile the source and to program the source, as I've shown you inside of MPLAB-X. And I can see from the lab that the LED has changed in terms of which LED we were programming. So that's what I wanted to show you. Go back to PowerPoint. Show you that you can create a program in GCSBASIC, take the source, use an alternative toolchain. You can then set the properties on that in that particular toolchain, program it, walk it in the debugger, etc. It works. Back to PowerPoint. That's a bit of an error. So with that, tomorrow I'm going to cover off a summary. And that summary will just pull this all together and potentially just reveal what I'm going to do next. So with that, I think we'll call that a wrap.